So today we're going to continue on the notes about boiling point elevation and after this freezing point depression. So what is this boiling point elevation stuff about? First of all, this is a phase diagram. And as you can see on the screen, I'm trying to see if this thing will advance to the next. I want it go. Okay, so anyways, this is a phase diagram here. The solid line is of pure water, okay? And the dashed line is if it were a solution. A solution like, say, for instance, it could be sugar mixed in water is a solution. And let me just pause for a second. Okay, sorry about that. Technical difficulties, but this is, the solid line is of pure water, and then the dashed line is if there was a solution, like sugar dissolved in water. As you can see right there, this is where it goes from liquid to a gas at, assuming 1 atmosphere. 1 atmosphere, if it was pure water, the temperature at which it goes from liquid to vapor state, meaning, what is that? That's boiling. Where does water boil? At water, it's at this point. But with a solution, it's slightly higher. The boiling point of a solution is higher, and it's always higher, is higher than that of water. If you dissolve something in water, the boiling temperature will always be higher. It's called boiling point elevation, that when you dissolve something in water, whether you dissolve sugar in water, by the way, we're assuming it dissolves. Whether you put sugar in water, salt in water, anything dissolved in water, the boiling temperature of that solution will increase. So the boiling temperature of the solution is always going to be higher than the boiling temperature of the pure water. The change in temperature, this little triangle delta, means change in the difference in boiling temperature, will be the boiling temperature of the solution, TB, minus the boiling temperature of the pure solvent, TB, and that, like, to the 0 power is also known as TB naught. But so TB naught, or just the boiling point of the pure solution. So since the boiling temperature of the solution is always greater than that of the solvent, the change in boiling temperature will always be a positive number, because the boiling point solution is always greater than, a bigger number minus a smaller number, doesn't matter what the numbers are. The difference in temperature will always be a positive number. Okay, so turns out we've done this with lots and lots of different substances. We found there's a pattern, and here it is. The change in boiling temperature, delta TB, is equal to some sort of constant Kb, also known as the molar boiling point elevation constant. It's a constant times m, the molality of the solution. So the change in boiling temperature, delta TB, is equal to a constant known as a molar point boiling constant. Lots of times we'll just call it the boiling constant. I'll even just call it the boiling constant. The boiling constant times m, the molality. Molality, as a reminder, we just did it. It's moles of your solute divided by kilograms of your solvent. So molality of your solution. That is a change in boiling temperature. Okay, what is Kb? Is not something you memorize. It is going to be a constant that will be on a table in a textbook. If this were a test, I would give you Kb. Just so you know, I'll look it up later. I believe the constant of water, it's, I think, like 0.51 or 0.52 Celsius per mole. The units will always be Celsius per mole, because the unit for temperature we're going to be using as Celsius, and this is times the molality, so per mole. Okay, that's the boiling point elevation. What about freezing point, though? Here's the same table, same graph. I just deleted all the pictures, or the lines there. The freezing temperature is where it goes from liquid to solid, or solid to liquid. By the way, freezing point is the same as melting temperature. Water freezes at 1 atmosphere, water freezes at 0 degrees Celsius, or it melts at 0 degrees Celsius, is the same number. At 1 atmosphere, water freezes or melts at 0 degrees Celsius. But what if you had a solution? You dissolve sugar in the water, anything, doesn't matter what it is. Notice the temperature on this graph at where it goes from a solid to a liquid state is lower. The freezing point of solution is always lower than that of pure water. It's also known as freezing point depression because it lowers, depresses, okay? If you had water and you put sugar in it, it doesn't freeze at 0 degrees Celsius, it freezes at a lower temperature. What is that temperature? We're going to get to the calculation soon, but it goes to a lower temperature. That's also partially the reason why we put salt on roads in places where it freezes. Not in Los Angeles because it doesn't freeze here, okay? There's no snow here. But in places where it does snow, where there's ice, you can put salt on the roads. It lowers the freezing temperature because you make a solution, and that solution doesn't freeze at 0. Maybe it freezes at 0 degrees. By the way, we're doing Celsius. It doesn't freeze at 0 Celsius. Maybe it freezes at negative 10 degrees Celsius. So if it's -5 outside, the sidewalk, your driveway, whatever, it wouldn't be covered in ice. It'll just be, well, it'll still be a liquid solution, okay? It lowers the freezing temperature. So you don't have to, the cars won't slip around as much or as easily. Plus the salt itself acts as, applies a little bit of friction itself. So it's kind of dual purpose of why you would ice roads in places where it snows or freezes. Okay, so change in freezing temperature, delta TF, is equal to TF naught minus TF, where each thing, TF naught is a freezing point of the pure solvent, T sub F is a freezing point of the solution. The change in delta TF naught is always greater than the freezing point of the solution, meaning the change in freezing temperature is always greater than 0. We do that so that, again, we have a positive number. But notice, again, it's TF naught minus TF. Okay, either way, the change in freezing temperature is equal to KF times M. The change in freezing temperature is equal to KF times M. I'm going to, in a second, go back and show you what's the difference between the boiling and freezing. And you'll probably notice that they're kind of the same. M stands for the molality of the solution. KF is called the molar freezing point depression constant. Or lots of times we just say the freezing constant. So they're kind of the same. Let me go back and forth between those two slides. So we have here, we have delta TF is equal to KF times M. What about the boiling one? It's delta TB is equal to KB times M. Freezing point. Let me try to get back there. Delta TF is equal to KF times M. Boiling one. Delta TB equals KB times M. Freezing one. Delta TF equals KF times M. Notice they're kind of the same, but they're not. They both have a constant. M is still a molality. The big difference is F for freezing, B for boiling. Boiling temperature always goes up. Freezing temperature always goes down. Boiling temperature always goes up, boiling point elevation. Freezing temperature always goes down, freezing point depression. Now, you're also probably wondering, well, what's KF and KB? These are not stuff you memorize, KF and KB. They are on a table. So for water, by the way, we are always going to assume water unless it's otherwise stated, the solvent. So what is KF of water? 1.86 Celsius per mole. What is KB for water? 0.52 Celsius per mole. You don't need to memorize these numbers again. They would normally be given to you on a test. But let's say, oh, you're not freezing water. You're freezing alcohol, pure ethanol. Okay? Then KF of ethanol, 1.99. KB of ethanol or alcohol, 1.22. So KB and KF, not numbers you memorize. By the way, we're always assuming at 1 atmosphere, so we're talking about at sea level. What if it's not at sea level? Well, notice this, if I have to slide this 1 atmosphere down to say, something lower, the boiling freezing temperature changes, so would the boiling freezing point of the solutions change. But either way, boiling point always goes up, freezing point always goes down. Just put that all back up. Okay, let's look at a sample question. What is the freezing point of a solution containing 478 grams of ethylene glycol antifreeze in 3202 grams of water? The molar mass of ethylene glycol is 62.01 grams. So, first of all, equation. The change in freezing temperature is equal to Kf times m. Okay. So, what are we freezing? It's not the ethylene glycol, the antifreeze that's freezing. It's the water. Remember, it's X in Y, solute in solvent. What is our solvent? It's water. It's the water that's freezing. So I want to look up on the table the Kf of water. Kf of water, you don't memorize this. It's right here. Water, Kf of water, 1.86 Celsius per mole. So that's the first thing you would look up. Okay. Again, on a test, you would be given this. Okay, well, the change in freezing temperature is equal to Kf, 1.86 times m, the molality. So that's actually not hard. We just need to calculate molality. Oh, molality, easy. Molality is the moles of solute divided by kilograms of solvent. Kilograms of solvent, water, we know. 3202 grams of water, but in kilograms, of course, that's divide by 1,000, 3.202 kilograms. The only other thing is finding the moles of solute. So how do I calculate the moles of solute? Well, to figure out the moles of solute, I'm given the grams of solute, 478 grams. How do I change grams to moles? It's been a while. You have to change grams to moles by dividing by the molar mass. Well, it says here, molar mass is 62.01 grams. So just divide by the molar mass. The 478 grams divided by 62.01 grams per mole. Grams and grams cancel. Oh, I guess it doesn't say it, but grams and grams cancel. Then you have moles per kilogram. Again, convert grams to kilograms by dividing by 1,000. And you get 2.41 moles. M, 2.41 moles. Delta TF is equal to Kf, 1.86, times M, 2.41. Plug it in. So 1.86 times 2.41 is 4.48 degrees Celsius. That's not the answer. That's the change in freezing temperature. That's a change in freezing temperature. Remember, freezing temperature always goes down. What is the normal freezing temperature of water? Well, you should know that water freezes at 0 degrees Celsius. If not, I mean, it is on the table, but you should know water freezes at 0 degrees Celsius. If it goes down by 4.48, if it normally freezes at 0, but it goes down by 4.48, the freezing temperature will be negative 4.48. Right, freezing temperature always goes down, boiling temperature always goes up. Okay, I'm going to pause for a second. Okay, there's one more thing that we need to know about freezing point, boiling point of solutions. And it's about colligative properties. And boiling freezing point are related to colligative properties. That is, colligative properties are properties that depend not only on the number of solute particles in solution and not on the nature of the solute particles. Sorry, they are dependent on the number of solute, I said not dependent. Some things include boiling point and freezing point. Okay, let's not worry about vapor pressure lowering right now. Let's just talk about boiling point, freezing point. And technically, there's another one that I skipped, about osmotic pressure. Right now, let's just focus on boiling and freezing point. So boiling point, change in boiling point is equal to Kb times m. Delta Tf is equal to Kf times m. M stands for the molality of the stuff dissolved in water. The only thing is, when we dissolve stuff in water, sometimes that stuff, like sodium chloride salt, when you dissolve in water, it breaks apart in water. They break into its ions. When I have 0.1 mole of salt in water, it breaks up into 0.1 moles of sodium and 0.1 moles of chlorine ions. What does it mean when something is soluble? When an ionic thing is soluble is that water rips it apart into ions. So the number of stuff that's dissolved in water, sodium chloride, is 0.1 moles of sodium, 0.1 moles of chlorine, or you have now twice the amount of stuff dissolved in water. And since boiling and freezing temperature are colligative properties that depends on the number of things dissolved in solution, number of solute particles in solution, that means when I have 0.1 moles of solution, I have actually 0.2 moles of ions, sodium ions and chloride ions. 0.1 moles of that plus 0.1 moles of that is 0.2 moles of stuff total. So we have to take into account that there is actually twice the amount of ions in it, twice the amount of stuff dissolved in solution. It's also known as a Van Hoff factor. Van Hoff factor I is the actual number of particles in solution after dissociation, means it dissolves or breaks apart in water, divided by the formula unit as initially dissolved in solution. It's actually kind of simple. First of all, if it's not ionic, I is just 1. How do I know it's not ionic? Nonmetals and nonmetals. Okay. Nonmetals and nonmetals is going to be ionic. Like sugar, C6H12O6, well, it's technically glucose, but C6, carbon, hydrogen, oxygen are all nonmetals. It'll be a non-electrolyte. But if it's a metal, sodium's a metal, chlorine's a nonmetal, then it's ionic. This thing is I is 2. There are 2 ions, 1 sodium, 1 chlorine. If I have calcium chloride, calcium metal, chlorine nonmetal, the number I is equal to 3. 3 ions, 1 calcium and 2 chloride ions. So I is 3. So the number of ions is equal to, or I is equal to number of ions that make up that ionic compound. So that's what that is. Okay, so when we're talking about boiling point and freezing point elevation, I actually have to also multiply by I, the Van Hoff factor. Delta TB is equal to I times KB times M. Delta TF is equal to I times KF times M. What is I? I is the number of ions that is calculated. We're not, ignore this measured one for now. That is calculator. HCl, 1 hydrogen, 1 chlorine. NaCl, 1 sodium, 1 chlorine. Magnesium sulfate, 1 magnesium. Sulfate is an ion. That's not 1 magnesium sulfur, 4 oxygens. It's 2. Remember, sulfate is one of those polyatomic ions. I know that goes way back to chapter 2, but it's a 1 ion. Magnesium chloride, 3 ions, 1 magnesium, 2 chlorines. This is also known as called iron 3 chloride, 1 iron, 3 chlorine. So 3 plus 1, 4. So I is the number of ions in that thing if it's ionic. If it's not ionic, like sugar is not ionic. Sucrose is not ionic. Sugar I is 1. If it's not ionic, I is just 1. Forget if there's, okay, we're not doing osmotic pressure. Yeah. Okay, so I think that is it for now.